So now that we've talked about atoms, the next step is to talk about chemical formulas, and then later on we'll be able to talk about actual reactions and chemical changes. So your book explains the distinction between a molecular formula and an empirical formula. This section especially focuses on molecules. So covalent compounds are arranged into molecules. We'll see a few of those below. Not every compound is arranged into a molecule. So some examples of compounds that are not made of molecules would be ionic compounds that we're studying in this chapter, crystal lattices that we're studying in chapter 10. For these kinds of compounds, the empirical formula, the simplest ratio of elements, is what we write as the formula. If something's not a molecule, the empirical formula is what we write as the chemical formula of the compound. All right, I just went ahead to chapter 10 in your textbook to find a little diagram of sodium chloride so I could contrast ionic and molecular solids. So sodium chloride is not molecules of sodium attached to chlorine. It's a collection of positive sodium ions, negative chloride ions, all arranged in a crystal lattice if it's solid, or floating off around in water if it's dissolved. So we don't have molecules of sodium chloride. It's not a molecular compound. Something like water is a molecule. It's not that we have just a collection of 2 times as much hydrogen as oxygen. We do have actual water molecules where there are 2 hydrogen covalently bonded to 1 oxygen. And we have discrete water molecules that are floating around separately from each other. This is the Lewis structure way to draw it. This is more of a ball and stick. I was trying to imitate that type of look. All right, so here we have an example of an ionic compound where the empirical formula is the chemical formula. The way that we express this compound is by talking about the ratio of the elements to each other. This is a covalent compound, so this is one that you could call a molecule. You can't really call sodium chloride molecules. So this one is a molecule, and in looking at this chemical formula, this is the molecular formula. It is the amount of elements that are in the molecule. It also happens to be the simplest ratio. So in this case, the empirical formula happens to match the molecular formula. But we do have some other examples that that's not the case. If the compound is molecular, then there can be a difference between the molecular and empirical formula because the number of elements in each molecule might not be the simplest ratio. Then this chapter also mentions the structural formula, and we take a look at isomers. We have a little problem down below. And these are more concepts that you would look at in organic chemistry. So we'll take a brief look at them below, but molecules and covalent compounds are things that organic chemistry tends to focus on more. So for these problems, we're going to first of all look and see whether these molecules are isomers of each other. If they are isomers, we'll just take a brief look and see if we can tell whether they are connected differently or whether they are just arranged differently, constitutional isomers or stereoisomers. To be an isomer in the first place, 2 compounds have to be different but have the same chemical formula, the same molecular formula. So let's see if these formulas are the same. These are organic compounds, so when we write the formula, it is typical to have the carbons listed first. And there are 6 carbons. When I count the hydrogen, there are 12 hydrogens, and then there are 6 oxygens. In this compound, there are 5 carbons, there are 10 hydrogens, and there are 5 oxygens. These compounds do not have the same molecular formula, and so these are not isomers. To be isomers, they would need the same formula. So if we look at B and we count up the different elements that are in each molecule, we can see that they both have 6 carbons, 12 hydrogens, and 6 oxygens. So since they both have the same chemical formula, they are either the same compound or they are isomers. If we look at this part of the molecule, we see a little bit of a difference here. This one has the O on the right side of the carbon, whereas this one has the O on the left side of the carbon. So these are not the exact same compound. Because they have the same chemical formula but are different compounds, then these are isomers. They're connected the same way. So this part where there's difference, these parts are exactly the same. This part where there's a difference, we still have the carbon that's connected to two carbons and a hydrogen and an oxygen. It's just that the hydrogen and the oxygen are on different sides. So same thing, this carbon is connected to two carbons, a hydrogen, and an oxygen. It's just that it's different sides. And so these ones are stereoisomers or spatial isomers. All right, for these two molecules, there's a little bit of a difference up on top. The bottom looks the same for both of them. These two are different molecules, they're different compounds, and yet they have the same formula. So both of these molecules have the formula C6H12O6, but they are different in their structure, and so they are isomers. For this one, the difference is a little bit more than for example B. If you look at this first carbon in the chain, it has 2 bonds to an oxygen, 1 to a hydrogen, and 1 to a carbon. This first carbon in the chain has 2 bonds to hydrogen, and 1 bond to oxygen, and 1 bond to carbon. So it's got different connections than this one. And the second carbon also has different connections. It's connected to 2 carbons and an oxygen and a hydrogen. This second carbon is connected to 2 carbons and then 2 bonds to an oxygen. So there's some different connections here. It's not just the same connections, but on different sides. There are some different connections. So since these are connected differently, then they would be considered structural isomers, not just stereoisomers. So again, this is something that would be focused on a lot more in an organic chemistry course, but I think it's worthwhile to introduce people to the concept that things can come in molecules and that 2 different molecules can have the same chemical formula. Then our next task here is for each molecule to write the molecular formula and the empirical formula. So all these compounds on this page have the same chemical formula, or the molecular formula, so this would be the molecular formula. And this molecular formula tells us how many of each element are in the molecule. For the empirical formula, we would want the simplest ratio. So we want to simplify this ratio of carbon to hydrogen to oxygen. So if you have a ratio of 6 to 12, if you have a fraction of 6 to 12, you can simplify it. You can divide each one of these by 6, and you can get 1/2. So 6/12 is the same as 1/2. That's what we mean by simplifying the ratio. If we divide each of these subscripts by 6, which we can do, we would get the simplest ratio of CH2O. The carbon and oxygen have the same amount, and the hydrogen is doubled compared to that amount. So back on this previous page, we had a different molecule that had a formula C5H10O5. This other one was still C6H12O6, but this one was C5H10O5. This would be the molecular formula because it shows the number of each element in the molecule. It's not the simplest ratio. We can divide each of these subscripts by 5, and we would come out with the simplified CH2O. Again, we have the same number of carbon and oxygen, and we have twice as much hydrogen. This is a very common formula for sugars, a common empirical formula. When sugars were first discovered, they looked like carbon with a water molecule attached to it. So that would be a hydrated carbon. And so that's where they came up with the term carbohydrates, because the first thing they discovered was the empirical formula, and they called that class of compound carbohydrates because that's what it looked like it was. I wanted to point out that you can sometimes have a molecule, and when you come up with the molecular formula, it ends up being the simplest ratio that you can get. So for this molecule, the formula is CH2O2, and we can't simplify that any further. We have a 1 to 2 to 2 ratio. So this also is the empirical formula. So it is definitely possible that the simplest ratio of elements is the same as the number of each element that's in the molecule. So they can be the same.